He's going to be talking about the Chord Lookup protocol, and the talk should be about an hour. Okay, it should be about an hour, and afterwards we'll have a bit of time to discuss amongst ourselves and ask John some questions, and the bar will probably be open again. So, John.
Thank you, David. Oh yeah, so the whole hour-long thing, we'll see how that goes. I'm hoping it's really going to be 45 minutes, to be entirely honest. I finished this slides half an hour ago, so I would have done more, but I'm a busy man apparently. So show of hands of who's read the paper? Who's read all the paper? Okay, so I can convince the rest of you that I know what I'm talking about. So Chord, the scalable peer-to-peer lookup service for the internet. So I'm John Allen, like David said. You can reach me at IamJSimmons on Twitter, although I'm really not on Twitter much. I just have it, so I kind of put a Twitter handle on my slide presentations. So I'm the CTO at a startup here in the city called Conference Cloud. And Conference Cloud is a virtual attendance platform for conferences. So, you can't attend a conference halfway across the world for whatever reason. You can still experience a really great, rich online, interactive experience online. According to the open source report card, which is this online service that kind of compiles stuff about your GitHub repositories, I'm a champion gopher. So I'm pretty much going to get a business card that says champion gopher. And that refers to the Go programming language, which is an amazing language, and I suggest all of you go learn it. And if you do learn it, then kudos to all of you. And I'd buy you a beer, but it's free, so Shopify will buy you a beer for me. I occasionally blog over at blog.jsimmons.io. Really just nonsensical stuff, super hyper philosophical, just no connection to the real world, but it's pretty fun. So this talk and why I'm familiar with Chord is because I'm in my spare time, which is few and far between, I work on a open source distributed file system, storage network I should call it, called Hermes. That man right there in the black shirt, and the man exactly right there. Also working out with him, and it's been really fun to kind of take the paper, which it's not a highly abstract paper, it's pretty down to earth, but to kind of take that and then implement it in actual code. Code's written in Go, by the way. It was actually a really fun process, and so that's kind of why I know, while I'm going to pretend I know what I'm talking about. Chord. Scalable peer-to-peer lookup system. So we can get into the nitty-gritties of really what each one of those words mean. Scalable pretty makes sense to all of you in that it scales to hopefully the internet scale. It's not just for people in a basement kind of using Chord and then after that it falls apart. So what is a distributed system? It's basically a system that's comprised of multiple nodes kind of doing one common task. And these are kind of the hot, popular examples of distributed systems. Mesos is a scheduler for a cluster of machines. CoreOS is this really cool kind of minified Linux distribution that's designed to be run across distributed systems. Raft is a consensus protocol. etcd is an implementation of Raft. React is a very, very cool distributed database. And I don't know why wrong is there, but again, I finished this half an hour ago. So peer-to-peer, not quite as common in terms of today's cool distributed systems, because a lot of the times most recent distributed systems, they've been created for the purpose of being used in production in infrastructure if they're for some purpose within a company or something like that. But and so kind of what peer-to-peer doesn't have compared to what distributed systems normally have is that it's entirely leaderless system, that every node in the system is the same as every other node, right? There's no no specialness to it. It's basically like the Karl Marx of like peer-to-peer systems, right? Everyone's just kind of equally sharing in the realm of what the distributed system or the peer-to-peer system is trying to do. But even though it's not like part of the cool, sexy kind of distributed systems of the days, it's still powers some very, very cool systems. Most notably, a lot of the Bitcoin and then altcoin technologies. It's entirely a peer-to-peer system, and that like no node in the Bitcoin network is special, which is pretty much why Bitcoin is as popular and amazing as it is. Torrents. So all of you, when you go and download your newest Game of Thrones episode and you don't actually pay for HBO, torrents is it uses P2P systems. And then a lot of distributed file systems such as GlusterFS, which is I know used quite heavily in actual production for a lot of companies, as well as the actual Hermes network, like I was saying, the project that I work on is a distributed file system, so it kind of works really, really well in that context. And again, because of the no leader, entirely leaderless system, then it results to a no single point of failure. So that's what SPF is. I think I meant to write that out as a full single point of failure, but yeah. So yeah, it's really great not having a single point of failure because, you know, it means that at any one point, and this kind of was our property of the distributed systems as a whole, but, you know, if you try to manage master leader type systems, there's a whole slew of algorithms to kind of facilitate that you always have a leader and, you know, your leaders are consistent, and there's just entirely realms of research around just the idea of that. So the fact that there's no leader, consequently, no single point of failure, and there's a lot less to worry about. Okay, so let's really break down what is Chord. So you can kind of think of it as a distributed hash table. And, you know, a lot of us should be familiar with hash tables because they're fairly, you know, common in most programming languages. For example, Java has hash maps and hash trees. The idea behind a lot of hash tables is that, you know, you have some sort of key, and then you can apply a lookup to get a value associated with that key. Yeah, so the really great thing about hash maps, usually in programming languages, is that they're very, very quick to do. You know, you can kind of do the same thing if you knew the index of an array. It's like I have an array of like apples and oranges, bananas, and I knew that bananas was that index too. It's kind of like that, but it's more down to earth. There's a lot more applications of just trying to manage indexes of an array. So you kind of get this key value map, which is really, really great in a bunch of systems. So other examples, Python has its dictionaries. Go has maps. And so, yeah, the idea of mapping keys to values is at Chord's heart a lot of what it's trying to do, as well as apply a kind of a routing mesh lookup system to map what it means for its own internal use of a key to what it means as a value. So some examples of distributed hash tables, kind of similar to examples of the peer-to-peer stuff, but DNS is basically a distributed hash table in a sense, in that, you know, if I'm going to look up google.com, when I go and my request is routed through the vast black magic box that is the internet, it doesn't use google.com the entire way. Basically what happens is if I go ask google.com, you know, what is it I'm actually looking for, the DNS system comes back and says, oh, google.com's IP is so and so and so. And the IP is, I'm hoping everyone knows, the address of a computer on the network. So like also GlusterFS, another distributed hash table, in that it takes keys, which can be known as, you know, names of files, or if you want to kind of different implementations of that, is that you can have, if you take the actual data of a file and use that as a key, that means you can kind of change the names and do cool stuff without having to move entire keys, which is kind of really nice. A lot of key value stores, which is just pretty much a lot of interesting databases going on right now that are distributed, use DHDs. And then Freenet, which is this kind of old school technology. It was old school, but it's kind of one of the earlier implementations of DHTs, in that it maps files to maps names of files to the actual data and where it's stored on the internet. But it does it in a kind of old school way. There's a lot of things that's missing, and the functionality and use of it's kind of few and far between. So why should we care about any of this Chord stuff? So the really great thing, and this is kind of what the paper goes through, in that like it's really key characteristics, because there are lots of other distributed hash tables and lookup systems out there, and peer-to-peer systems that facilitate this. But what Chord really likes to say that it has really good going for it is that it maps keys, so whatever we want the keys to be, to actual nodes, which is some node somewhere on the internet or in your distributed system. So you can think of the nodes as the actual values, but nodes is slightly different than actual values, because you start doing other things once you have node IDs. And so on top of the actual translation between keys and nodes, it actually does the routing throughout the interwebs for when you want to find a node. And so basically the idea is, if I want to find a node responsible for some key on the network, I ask Chord, like, hey, I have this key, call it John. Where is the node, or what's the node identifier that's responsible for that key? And then when I have that, I can send messages to it using the same message, the same functionality that kind of the internet uses, and that it hops from node to node to node. It's a really simple protocol. Maybe some of you going through the paper will be like, this is the fucking complicated thing ever. But it's relatively simple compared to other kind of lookup systems and distributed systems as a whole. Like, again, distributed systems is a very complicated realm of things. So in the scheme of things, Chord's relatively simple. And because of its simplicity, it's actually provably correct. And we'll go through some of the proofs. And you can point out how entirely wrong I am and zero understanding of this paper. But hopefully that doesn't happen. And so one of also its consequences of the simple protocol is that it actually has really good performance. And we'll go into, what that performance is and why, despite a whole slew of things you usually have to deal with, it can maintain this performance as it scales. So that's kind of one of the key words in the name of the paper, in that even if you have a very, very large network, Chord will still handle this great performance as the network grows. So that's really great. And so not only is it great performance and provably correct, but it's has both of these under high churn. And churn is basically the continuous leaving and joining of nodes into the network, right? So usually in most, if you're running a Mesos cluster, you don't really have to worry about all the time nodes coming in and leaving, because the idea behind that is that you have this cluster of machines. Every now and then one of them will go down. You'll bring up a new thing to handle scale. But one of the kind of characteristics of a strictly peer-to-peer system, and you see this a lot like in torrents and Bitcoin, is that nodes come and go all the time, right? Think about the number of times you open up your torrent application, I'm a huge advocate for Bitcoin. I use it every day, and I have a Bitcoin node running on my computer or my laptop, but I'm always opening and closing it. And so, to be able to handle provably correct performance and correction of the actual algorithm under this high churn load is a really key and pretty much required property of a good peer-to-peer system. And Chord likes to say it is one of the forefront runners in the relative to other peer-to-peer lookup systems. It's a really great protocol. And even the few times when you do kind of have your efficiency degrades or your performance degrades, when starting with a few certain instances, it degrades really actually well and degrades rather probabilistically. So that's a really, really great thing to do. And then lastly, it's not like to maintain all of these really great things, you have to know like the entire state of the universe, like every quark and string, and it's actually really quite simple. You only have to maintain the information about a certain subset of nodes. So KV, all the things. Like I said, examples of KVs, hash maps, dictionaries, maps. Take a key, map it to a value. So this kind of like where the preamble stops, and we kind of start getting into what Chord does and why it does it and how it does it. So given some k or key K, and the key can be anything. What's one of the great things about Chord that it requires no naming structure across the entire what you call a key, right? So it can be a string of bytes, it can be a string, it can be an int, it can be whatever it is you want, as long as you can call it a key and apply a certain type of function to it, then that's your naming scheme, right? So you don't have to have like a schema, you don't have to have some other like restriction, you have to have like certain number of characters in your keys. It's entirely great in that sense, where you can just use anything as a key, right? So to go back to things, so given some key K, return the node in the DHT, so the Chord network, responsible for that key K. So that's its first functionality. And the other one is route the message through the network to that node, right? So if I want to send a message to, David at the back, who's just, quietly sitting there, if I want to send a message to him, if I knew his node identifier, then I can route my message to him. And as we stated before, we can actually route it rather efficiently, right? So I wouldn't have to go to each one of you and be like, psst, tell David so-and-so, right? So that's really, really great. So some of the design goals of what Chord tries to do and tries to accomplish is it tries to be load balanced, decentralized, scalable, and have high availability, right? So these kind of like, if I was putting together a distributed system, I'd be like, yeah, I would love to have all of these, but apparently it's kind of hard to do it. I think this is the only slide that actually has animations. Don't ask me why. So, some of the examples of, and I kind of go through a lot of examples so you can really ground, and this is what I did when I was learning the paper. You go through a lot of examples of what it means to be a DHT and what you can do with it and stuff like that. So, a distributed storage system, which I won't get into because I've already kind of done that. So this is in the paper, like one of the examples of what you can do with it. It has a very cool name, large scale combinatorial search. Very cool. And the idea behind that is, if you have some sort of candidate solution to a problem you're trying to solve, then you can use Chord to give you the machine responsible for testing that candidate solution, which is pretty cool. I think this slide should have been before, but here we are. So, maybe you have a distributed IMDb for whatever reason, and you map, movie titles or kind of other search queries to a key value type system. So if I in this system wanted to say like, hey, what's the greatest movie of all time? Of course, the answer will be obviously The Matrix. So I don't know. In fact, all of you should just be at home watching The Matrix, not being here, because clearly you're just wasting your time not watching The Matrix. Okay, so let's get into the meat of things. Yeah, that's right. I was going to do a picture of raw meat. For starters, don't Google raw meat. So I kind of scaled that back and was like, hey, let's do cooked meat because it's slightly better. Although this is still rather a rare steak or whatever. So how kind of does Chord do what it does? Well, first we talked about, given some K key, it maps the key identifier, or maps K to a node identifier, and it also routes that message to the node identifier through the network, right? So in the simplest possible way, and this is kind of the initial protocol, initial way that Chord presents how the system works, is that, when you guys were little, did you ever play like Stella Ella Ola? All of you kids kind of like went in a circle and you clapped hands together until, I can't remember how the rhyme goes or what have you, but basically the idea is to slap the next person as hard as you can. If someone slaps out a certain word, then they're kind of out. So that's the idea behind Chord, right? So you have all these nodes, and the easiest way and the easiest way to maintain correctness in the network is that, just keep on routing to the next person that you kind of should be routing to. And that's the only requirement for this is that I only know about, one person, right? So if I went to talk to David at the back, I would only have to know about one of you. Okay? I would only have to know about one of you, so long as each one of you knew about the next succeeding person in the line to get to David. And eventually we'll get there, right? It may take I might start here and David might be there, and I can only go this way, but I will get there. Now, some of the problems with this we can get into. So, do you even map, bro? That was a terrifying picture I found, and I figured it was rather appropriate. Now, this whole Jeopardy thing is supposed to be a transition, and it's not, so it seems oddly anticlimactic, but whatever. So, how does it do this mapping from keys to node identifiers? Well, you can kind of think about the namesake of what it is, a distributed hash table, right? So the keyword there, again, anticlimactic, is that hash, right? So hash functions is a whole realm of cryptographic, well, not usually cryptographic, not required to be cryptographic functions, but they're awfully used in cryptography. And we'll get into what exact hash function is. So yeah, anticlimactic. Proofread your slides. So, hoping all of you remember your wonderful linear algebra from school and whatnot. It's easy for me because I was doing it yesterday for school. So yeah, the idea behind a hash function is that you have some function that takes a key and maps it to it should be another, shouldn't say node, it should say some hash of the key. But in the case of Chord, the hash function takes the hash of the key, and that is your node identifier. It's very simple, and that's how it maps keys to node IDs. Now, this is similar to the way you can kind of map vector spaces, and it kind of makes sense to talk it in that sense because when we're talking about the size of your hash, which is a very important property of Chord, it makes sense if I have my vector space in R1 and I'm trying to map that vector space to R7, then the sizes of those and can one fit in the other, and so it's kind of like how hash functions come to be. Does anyone know like the simplest? Well, I don't know about the simplest, but like a really, 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 really simple hash function. No. Pardon? Yeah. So that has no reference to what any of this is, but I went searching for like the simplest one, and I feel like there's one simpler than modular, but I couldn't find it. So modulo. So like I was saying, the size of the hash function, like what does that mean, right? Because it's like if I have the size of SHA, is it like the number of characters that it used to make the name the hash function, or some other weird way of describing like the size of the hash function? And so the size hash function is basically dependent on the number of bits you use to represent your hashed keys. So you saying the size of SHA is a very poor question, because SHA can take on a number of different sizes. It can be 128, 256, 512, so on and so forth. And so what it means to say the size of a solution space is that you take the number of bits you have in that, and you take 2 to that number of bits, and that's your overall size, right? So if I had a solution, or if I had a hash function that basically mapped things to 0 and 1, then my solution space would be 2 to the 2 or whatever. Sorry, that's not right. But I'm just gonna pretend it's right. So the bigger the hash function you have, in terms of the bigger or the more number of bits you need to represent your keys, the better in terms of the Chord paper and functionality and protocol. So the other really great thing is, or required thing, is consistent hashing. And so this is not a representation of consistency. And so you need consistency, and it basically relates to probability, right? So a consistent hash function is one that with high probability, or under something else that's called the hardness assumption, I'll use the hardness assumption. So with the hardness assumption, you're going to have a uniform distribution, okay? So a uniform distribution of keys to values in your hash function. So that means if you just keep on pumping more and more and more and more keys into the hash function, the idea is before you have any kind of collision, and a collision is when if I have the hash of apple and the hash of banana, they both result to the same thing, then that's a collision, because that's bad in the context of this. So the idea of consistency or the consistent hash function, and this is also the same with a uniform hash function, is that it kind of maps to the entire solution space before it starts repeating. The also other requirement of hash functions, which I didn't actually show you, is the fact that if you hash the same thing, then you're going to get the same value. Sorry, I didn't cover that. Very, very important. Kind of breaks down otherwise. So what does hashing have to do with the concept of a distributed hash table, specifically in the case of Chord, right? So what you do is you basically construct what's called a hash ring. And a hash ring is you take the entire solution space of all the possible hashes, and you basically loop that in over itself, right? So if my hash function mapped whatever it got to the values between 0 and 15, then this is what the hash ring might look like, right? So you start at 0, go all the way down, 7, 8, 9, 13, 14, 15. What do you get at the end of your solution space? Well, you wrap that back to the beginning. And the way you do this is all the arithmetic and all the computations in Chord are actually done using modular 2 to the m, where m is the number of bits of your hash function, right? So what that results in is a nice hash ring that continuously loops over itself, right? Which is really, really important. So let's get into what a hash means with the association of keys and node IDs, right? So if this is my entire solution space for my hash function, then like I said, this is my entire network of the Chord system. Now, if I have a hash function that's like SSA 256, which has 2 to the 256 number of solutions in it, the number of keys I have is absolutely massive, right? But that doesn't mean I'm going to have that many nodes in the network. I can have as many or as few nodes as I want, right? Usually if you have 1 or 2, it's not really a distributed peer-to-peer system. Well, 2, yes, but not 1. So in this, all the blue nodes, or the blue circles, are represented by actual nodes in the network, and the clear or the white ones are just potential keys in the solution space. So the idea of Chord is, I was saying the thing about succession, right? So if I want to send a message to David, I send it to one of you, you continue to send it to your successor in this line, right? So if I was here and David was up there, I kind of send this along the network. So, what does it mean? Which one of you would it be that you are my successor that I'm supposed to be sending it to, right? So the idea behind that is that if I have a node, like node 3, node 8, node 10, node 15, the successor of a key, okay, so the successor of the key is the first node in the network that is equal to or succeeds that key k. So if I was trying to look, who is the successor of key 2, who would that be? It'd be 3, obviously, because it's the first node that is equal to or succeeds the k2, or the key 2. And so the easiest way to think about this is, if this was a clock, which is very easily understandable that it was a clock, if I was going counterclockwise, sorry, am I using this? Is this keep on okay, cool. So if you started, if this is a clock, if you're going counterclockwise, if I started at 2, what's the first node? And remember, nodes are blue. So what's the first node I would hit if I was going clockwise, right? So if I started at 2, the next one would be 3. And that's what it means to be a successor in this weird hash ring type thing. And that's very important in the context of Chord. Okay, so, now what? Now we have this notion that we can take keys and do this weird kind of hash function to it, and, we get the ID of some node that's apparently responsible or apparently the successor of such key, right? So kind of what do we do with all this useless junk, which is useless until we actually have some use for it, right? So again, the idea is if I'm sending the message to David, right, all that hash function stuff was that I now know how it is I refer to David, right? So if I take the hash function of whatever and apply what's the hash of David, and I get back if I get back 2, then I know David, or the node responsible for David, is 3, right? So the way the protocol works in this context is that each node n, so each node n maintains a pointer to a successor, right? So the idea is I always know if I'm trying to talk to someone in the network, right? So if I'm 14, I will always know who my next successor is. Like, it may change, and the protocol will always update. And if a new node came in at 1, right? So if a new node came in at 1, and I'm 14, I would eventually, through basically what the protocol is, know that my successor is 1. But the key thing for correctness, like we showed in the Stella Ella Ola example, is that you have to know who your next person is. And eventually, although you might traverse the entire network, you'll always get to the node that you're trying to talk to. So I said, continuously pass some message from successor to successor to successor to successor in the Stella Ella Ola-like fashion. And eventually, we will reach successor k, which would result in the node responsible for the matrix. And like I said, this is guaranteed correctness, right? Unfortunately, it is terribly inefficient in that it takes ON traversal, which, for all you data structure algorithm theorists out there, is in some cases ON would be great, right? Like if we had a sorting algorithm that did ON, that'd be dope. But in the case of routing and routing protocols, ON's really, really not good, right? So if I had 1 million nodes in my network, it would take 1 million steps to get to the node I'm trying to get to, and that would be not good. Right. So in that context, this is what I didn't notice that, so that should be fixed. You could ignore that. 8 should be pointing to 10, and 10 should be pointing to 14. But I think I had a can of pop in front of my screen. I'm going to blame that. Okay, so like I said, so ignoring this, the idea is 3 knows about 8, which knows about 4, right? So if I'm looking for the successor of key 6, for example, so if I'm looking for the successor of key 6, I know it should be 8, right? Because I'm at 3, and there's no one between 3 and 8 as far as I know. So therefore, like we said, the definition of the successor for key 6 is the first node greater than or equal to 6. So that'd be 8. Okay, so that's it. We're done. We have all of our, no, I'm just joking. So like we said, we have correctness. Our routing protocol works. We have keys to nodes, which is great. But ON sucks in the context of this, right? So Chord's like, we can do better. And there's also a whole section that we haven't got into yet, which is, in this example, we already have, a network. Right? We have no idea how it became like this, but we have it, right? So a part of the Chord protocol, is how do we construct this, right? So if we just started with 3 and some crazy notion of a hash ring, if 8 or 10 or 14 or any other node joined, how do you construct this very beautiful ring, right? And so what the finger table tries to do, which is not the joining side, which we will get into, is basically address the efficiency problem, right? So we have correctness, which is great. Around and around we go, Stella, Ella, Ola, successor, successor, successor. So how do we do better than ON? Well, it turns out that if we maintain a little bit of information about a certain number of nodes in the network, then we can highly accelerate the routing of a message throughout the network. And we can maintain provable correctness. Okay, so that's a really important thing. The whole ethos about we'll keep on returning to this is maintaining provable correctness under basically everything we do, whether it's trying to optimize the speed of the lookups, or we're trying to figure out how people join, we're trying to deal with failures. All this is required, or one of the required properties, that we still maintain our provable correctness, right? So how do we what is this finger table type thing? Like, why the fuck is it called a finger? So like I said, if we maintain a certain amount of information about a small subset of nodes, we get all of this, which is really, really cool. But specifically, if we maintain information on M, which is the size of the hash function, remember we talked about that? So in the case of before, the hash function has a size of 16, right? So if we have the size of the hash function, we know what M is. And so we have to maintain information on M many nodes. Now we don't know which nodes quite yet, but we just know, there are an M many number of you that I should know that if I want to send a message to David, then it's going to be rather efficient. So we define the finger table as this. For some node N, the ith node that N needs to maintain in terms of information is defined as the first node that succeeds N by 2 to the I minus 1. Okay. Modulus 2, because that's where we do all of our arithmetic to maintain that hash ring type thing. Right? So what does this mean? What is this maintaining information on the first node? It sounds kind of weird, right? But an example here, where is it? What is the successor of 2? What is the successor of 8? What is the successor of 15, right? So when we say the successor, or the first node that succeeds N by 2 to the I minus 1, we call this the successor of N plus 2 to the I minus 1. Where N is, if I'm some node N, I have some identifier that I refer to myself as. And so that's what we do. You take the keys that were kind of basically hash, and we add 2 to the I minus 1 to it. And we call this the ith finger, not finer. It should be the ith finger of N, right? And so this is represented throughout this talk in the paper as n.finger index I dot node, right? So the ith finger, in N's finger table, and then the dot node is because the finger table can require or maintains extra information. But so the ith finger of N is represented as that. And so it's easy to note that, if I was 1, also I think this, yes. Here it says 2 to the I minus 1. Here it says I plus 1. That should be I minus 1. Sorry about that. So it should be easy to know that the first finger, right? So what is everyone looking at? The first finger of N is the successor of N, right? So if we have 2 to the I minus 1, and we have 1 as our first finger, then 2 to the 1 minus 1 is 2 to the 0, and anything to the power of 0 is 1. So that's kind of why the first finger of N is the successor of N. So this is kind of what the finger table, in a loose kind of sense of the word, what it is, right? So if we started off with node 1 here, right? We start off with node 1, and we maintain M information, right? So if this is our hash function, then we have 8. So the hash function is size 8. So that means our hash function is 2 to the something, which equals 8. Happens to be 3, right? So each one of our nodes need to maintain information on 3 other nodes. Now, it's going to sound like what is the advantages of having this weird finger table type thing, right? Well, some of the properties we get when we do know N information on the certain many number of nodes, which is I, the successor of N plus I to the I minus 1, is that it turns out that we know more about nodes close to us in our local kind of region of this vast network than we do about nodes further away from us, right? And so that picture is kind of like a representation of which nodes we happen to know, right? So clearly it's obvious that, those first 3 nodes are kind of close in my region, and that last one there is, further away. So we know more about our local nodes than further ones. Also, if we pick some arbitrary key, I'm going to keep on making that mistake, but I'll try not to. So if we have some arbitrary key k in a sufficiently large or sufficient network, then we're probably not going to have that key in our finger table, right? So we're probably not going to know about it if we only know about m number of nodes in the network, right? So if we have our hash function, which is SHA, and our solution space, or the size of our Chord network, is 2 to the 256, sorry, SSA 256, right? And we only know about m number of them, which is 256, the number of nodes we know relative to the vast number of nodes that can be is very, very little, right? So we most likely won't have some arbitrary key k in the table. So if we don't know or if we don't have this key k in our finger table, what good is it? And it turns out we're either in two camps, right? We're in the small chance that the key k is on our finger table, in which case this is great because we just send it over to the person we're trying to, right? So in this case, if I'm that first node there with all the fingers coming out of it, and I'm talking to David, and David's right here, I'm like, oh, that's easy. I know where David is. He's right there. So I'll just send it to him. Now, the more likely case, like I was saying, did I do something? It seems darker. Look what you've done, David. Is everyone still able to read this? Okay. Sorry, I thought my running across the screen broke something. I'm like, wow, that's impressive. Oh yeah, so like I said, so the more likely case is that k isn't in our finger table, and then what do we do? What do we get out of that, right? So it's easy to see how our lookups can be accelerated if k is in our finger table, because instead of having to make, 1, 2, 3, 4, 5, 6, 7, 8, 9 hops, we only have to make one, right? But if it isn't in one of these many number of entries in our finger table, what then? Well, it turns out that we can find the next closest person who is closer than me to David, right? So what does that mean? It turns out that we can always, for any k key, we can always get closer and closer and closer while still jumping a whole people in this number of line, right? So I'm going to keep on using this example. I'm sorry if this annoys all of you, but if I'm trying to talk to David, I no longer have to jump through all of you, right? I know that one of you is in my finger table, more specifically, m of you is in my finger table, right? And I can talk to the person who I know is the closest person to David, even though I don't know where David is, right? I know David's identifier because I just take the hash of David, right? But I don't know where he is, but I know that one of you is closer. And so what we define this as is we forward the request to the closest person we know, right? So I know m of you. There's going to be m minus 1 of you who I don't care about. So one of you is closest than all the other people I know to David. So this kind of in terms of means, what does it mean to find the successor on the network, and what does it mean to search the finger table for said node, right? So this is kind of the pseudocode that's represented in the paper. It's almost I think it's a one-to-one. I don't think I did anything, except for maybe didn't use Greek symbols for some of it. So finding the successor of some key k. I'm gonna take a drink every time I do that. So in this new notion, instead of routing next to next to next to next to next, right? If I want to find some key k, I'm going to actually find the predecessor of him, and he's going to route that last hop, right? Now again, I might not know who the predecessor is, and it's likely the case that if I don't know who the actual node is I'm trying to talk to, I won't know the predecessor. But let's kind of go with this notion that we always want to find the predecessor of the k key, and he'll take that last step, right? So find successor is defined as that, right? Find the predecessor, whatever it may be, however you may do it, and then return its successor, who is our key K. So find predecessor is defined as this. We start off with ourself, right? So we start off with ourself, and we continuously loop. Okay, so we continuously loop so long as this is true. And this states that for some ID, so basically for the hash of David, if we have the ID and it's between whatever n prime is, which in our first iteration is just ourself, right? So if it's between n and our successor, then, if it's not between, then we stop and we basically return, right? So in the case that if David was my successor, right? So if he happened to be right here and I need to talk to him and I did this long, instead of realizing that he's right here and I did this long thing, right? I would realize, I'd start with myself. This wouldn't happen, this would happen. This would be false. This would be true, minus the not would be true or false. So this is true. And we just happen to talk to the person right next to us. In the sense that, remember, we always talk to the successor, whoever we find, right? So this iteration, if David was right beside me, this iteration would return myself. And I knew who my successor is, and so I just send it to him, who happens to be David. Imaginary David sitting right next to me, right? But if it isn't the case that David's right beside me, what then? Well, we kind of find, like I was saying, the next closest node that I know of. Okay, so the next closest node I know of that is closer to David than myself. And so we do it using this. That should be an underscore, but it's not. Again, proofreading, guys. Don't wait until the last moment to do your slides. So we use whatever this, and the idea is that this returns the closest person in my finger table that I know of to David than myself. And then we return him, and then his successor. So that's the idea behind that, right? And this will continuously kind of work, right? So if in the context of n dot find blah, 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 this is represented kind of as an RPC call, right, for example. So that's why it's easy to represent n prime dot closest preceding node in the sense that, this function is being called on this node. So this is being called within one node n. So that's kind of what that means. I should have prefaced that, sorry. Oh yeah, so what is closest preceding finger table? What is any of that? Well, we basically start with this. We start with the largest largest ID or key in our finger table, and kind of we work down from that. Because it turns out that it's more likely going to be the case that we find them further out than closer in. Right, so we start with for I, m down to 1. Look at the finger, right? So which one of you, if I'm looking at all of you, and I know, you are in my finger table, and it happens that you, William right there, happens to be the closest, right? And he's at I equals m. And it turns out, then I can just return him, because he's the largest person in my finger table, and William's we'll take the request from there. He'll find the next closest person. Right, so if it's not William, then I go down my finger table, and I find the closest person, right? Because it could be the case, because we know more about people local to us than further away from us, it could be the case that the furthest person out we know is actually too far. So we're going to back that up, right? So we just want to find the closest person preceding David, right? So that's what closest preceding does. It goes down the finger table and finds the closest node it knows of that precedes the ID, which happens to be David, that we're trying to talk about. Right? So if this was our finger table, right, and David is at node B and I'm at node A, then I know that if I started down this iteration, this pseudocode type stuff, and I got into closest preceding finger, I got into this routine, I would start with I equals m, which happens to be this guy, right? And it turns out he still precedes David's ID. So I would send it to him. And then that node would continue along this same process, right? So A would go to whatever node that it knows of in its finger table, and then that node would repeat the process again, and it turns out he can get to someone even closer to David, because it's probably the case that he doesn't know of him. But eventually, in the same way that we go down the Stella Ola, eventually we will get there, right? And it turns out that eventually, like the performance of that eventually is really, really good. Okay, so this is like the one actual proof that we're going to go through. And it's not really proof, it's just going through the words. Right. So the theorem is with high probability, and this is actually associated with the hardness assumption, right? In the original paper, it references all of this stuff from a different paper that uses a collection of hash functions. And so you can do the same with high probability in that sense, or if you have, say, SHA-256, the hardness assumption says it's very, very hard to know the input such that you can get the hash of that are close together in that identifier ring, right? So it would be very, very hard for me if I wanted to be here, right? And I knew if I decided to figure out some key K, right? It'd be very hard for me to exactly figure out this, because you'd have to reverse an ideally irreversible function, right? So the idea is that you can not reverse the function of a hash function. That's the ideal case. So that's what the hardness assumption is, that it's hard to do. Okay, so with high probability of the hardness assumption, the number of nodes that need to be contacted to reach some key K is O log n. And that's really, really great. That's much, much better than ON, right? So if you're, the easiest way to think about that is if you have a binary tree or a binary search tree, then we know, because we've all taken data structures, yes. Sorry. We know that, we can continuously cut down half the number of people that we have to search through, right? So if we have this big, long table, and sorry, I was actually hoping that we had a whiteboard, but that's fine. So if we had this big, long binary search tree, each node in the tree has two child trees, then every time we go down that tree, we cut down half the potential, or half the number of nodes still available in that tree, right? So that's the easiest way to see like what it is that O log n is. And that's very easy to see in this example, because to get from A to B, the first step we took happened to wipe out all of the, like, half the node. Okay, how much time do I have left? Well, you put up 9, right? Pardon? Okay. So I don't know like when this is supposed to go to, so I'm just gonna keep on talking until I'm kicked off the stage. Right? So it's very easy to see going from A to its next finger table that it's gonna cut out half the people. So that's the same case, then a binary search tree cuts out half the possible thing left over, right? So now, if it was the case that our entire network was really just the nodes between this guy and B, then the next operation is also going to happen to cut out half the guys remaining, or at most half of our guys remaining. So it turns out that you keep on doing this, and we arrive at O log n. So it's easiest to understand what O log n is, and it's easier to show or see that that applies to the number of messages it takes to go through the network. Okay, so do you want to go through the proof of this, like steps? I don't know. David's saying no. Is that a 1?
That was actually the question.
Oh, okay.
What's the low probability case?
Pardon me?
What is the low probability case?
Are you saying with high probability this?
Right, but what happens with low probability?
So the low probability that the distance that we cut out half the people, or the low probability, oh, okay, so I see what you mean. So the chance of that happening with low probability is that it takes O log n, and I don't know what the actual, like, assuming, sorry, it takes more than O log n, right? So it could be the case, and it's further down the talk and represents this, it could be the case that because of the constant churn of the network, right? It could be the case that we have to talk to every single person.
So if we're not connected the way you described.
Right, exactly. Or the way we described is out of date, right?
So the probabilities aren't actually in this proof, right? This is a proof with absolute certainty that we will have O log n behavior.
Exactly, yeah.
The probabilistic aspect comes in because we're usually connected in this way, but may with low probability be not connected in the way that you described.
Exactly, right, yeah. And that relates to like also the constant like changing topology of a network because nodes are coming and go in. But also in the case of this, because like I was saying, the high probability and the hardest assumption are that it's hard for like someone to manipulate the location of nodes, right? So it's most likely not going to be the case that all the nodes are like in this small section, right? So instead of being all of this, right, the nodes are just in this small section. So if that was the case, then when we got from A to B, or A to this guy, we call him C, then it could be the case that we have like a bunch of nodes to talk to, right? So the hash function dictates that with high probability or hardness assumption, then they're going to be evenly distributed, and so therefore this is probably going to be the case. Yes? No?
Are you saying one of those blue dots would represent many different computers?
Right, so a node, right? So if this, so in this case, like every blue dot is a node. In our other case, like every white dot was a key, right? So in this case, the entire network is filled up. Now it could be the case, and sorry, it's a poor example of it. It could be the case that, like I was saying, between C and B, there could be a lot of, for example, if every single like pixel here was a was a key in the hash ring, right? And our nodes are evenly or uniformly distributed across the entire network, right? If it wasn't the case that it was evenly distributed, right? So the hardness assumption didn't exist, and we could have it such that someone could manipulate the system so that nodes pretty much only existed between A and C here, or B and C here, then it would be the case that it would take longer than O log n. But because the hash function, the uniform consistent hash function, dictates this uniformity, that's where the probability comes in. So, David, you're saying that we shouldn't go through the proof? Well, I don't know how much time we have.
How much time did you want to take?
I have no idea.
Well, it's been an hour, so
Is it really? Jesus Christ.
for a while longer.
Okay, we won't go to the proof. It's a very simple proof. We won't go through it. It basically just involves the fact that the distances between the number of people you keep on jumping happens to be half the distance. And if you continuously do that, then we arrive at O log n. Okay, so what do we have so far? We have a method for mapping keys to nodes using this hash function. We have a simple method for routing requests around the network, which is the Stella Ella Ola successor, which is garbage because it takes ON. And we also have an efficient method for routing requests around the network, as long as we maintain a certain amount of information, specifically M, information on M many nodes along the network, in which case we can do it O log n. And O log n is much better than ON, and so technically we could be like, okay, we're done as well. But like I said before, all this has never at all talked about how we construct this, right? It just states that, given an already existed Chord network, how do we do the routing, right? So how do we build and then maintain this network? Okay, so apparently, Chord works great under churn. So like I was saying, and this is one of the original statements it makes in the paper. It works really, really well when lots of nodes are joining and leaving. And so the way it defines working really, really well is that it's still provably correct and provably efficient. But we need to now devise a method that allows to join the network and allows messages to be routed still with the above requirements, right? And so when a node joins the network, we can maintain and build this weird finger table, which allows us to do that efficient hopping. But apparently we need one extra piece of information now, right? So before we kept track of M many people, we always kept track of our successor, right? The key to the correctness of the algorithm is keeping track of the successor. But now we also have to keep track of our predecessor, right? And that who is behind us in the network. Because it turns out that's pretty useful. So kind of a simple method for how the join works is if I'm node n and I know that there is another node in the network. I somehow got his IP, and I can talk to him, right? Because the internet is reliable, right? So if I know of some node n prime, I can ask him who the successor of my ID is, right? Because if I know who the successor of my ID is, when I join the network, he's then going to be my successor. And this is how it works, right? So if my successor is S, then when I jump in, he's going to be my successor because, sorry.
Where does your ID come from?
So the ID comes from the hashing. Oh, it's like if I personally did it, right? So if a node just wanted to join the network, is that what you're saying? So like that's up to the discretion of the application that's implementing Chord. The easy example is to use your public IP, right? Because even though like for some reason your network of people might not be like a uniform distribution of IPs, the hash function will, through hardness assumption, make that uniform. But there's lots of different examples. Like in the example of Hermes, the distributed file system, we use private keys and stuff like that. So it's kind of up to discretion. And again, they don't have to be uniform because they become uniform, right? Yeah, so then what happens once I actually join the network and I know that S is my successor? He doesn't know about me, right? But I know about him. So am I really part of the network, right? Is the cat dead? Is it alive? I don't know. So what I do is I just tell him outright, like, hey S, I'm your successor, right? Because now I'm in the network, right? And I know node S, so therefore I know the information required to talk to him. I send him a message saying, I am now your predecessor, or at least I believe that I'm your predecessor, right? So now that we're in the network, which is all great, we now we have to construct our finger tables so that we can provide this efficient lookup, right? But we already have provable correctness because the idea is that n is now the predecessor, or even better, S is the successor of n. So in this context of routing messages around and around and around, if a node or message happened to come to us, or we want to send a message, we can still send that message because we now have the only requirement, the only invariant, if we want to go into the technical word that we reference in the paper, is that we know our successor. Successors are equivalent or are known, right? But so let's figure out how to actually build this finger table so that we don't have to do ON steps. So it's actually rather easy. So it turns out to initialize the finger table, we know M because we're given this hash function because we have the software that allows us to join the Chord network. It's all the same software, remember, peer-to-peer system. Right, so we know the size of M. And so it turns out that we just go and just figure out who they all are. Like we ask exactly who the successor is for every node in that finger table, right? This piece of code basically just says like, it could be the case that a bunch of fingers have the same successor. So this is kind of like a shortcut. But the rudimentary version of like thinking about it is that we just go, we say, oh, this ith finger in the finger table is, is at 2 to the I minus 1. And we just ask who is the successor at 2 to the I minus 1. And we just build it all up, right? Now that's a brute force kind of dumbish way of doing it, but now we have our entire finger table, right? But it's also the case that now some of the nodes already in the network, because we're now a new node in the network, it could be the case that they have to fix their fingers because we kind of popped in there and where they thought was someone is now somewhere else, right? So the fixed network fingers goes through everyone who I now know of in my finger table and tells all of them to update, right? And then when they go update, it turns out that they might have someone, usually now their predecessor, who now needs to go update as well, right? And around we go. So technically, this works, and we have our finger table. And given enough time, and if this is the case that only one node joined and then the entire network did the stabilization, right? It could be the case, or it will be the case, that eventually all the nodes will have their now finger table, and the new node n is now joined, and all the successors work, and we have provable correctness, and we have provable efficiency. But again, one of Chord's really great thing is that it's supposed to work great under high churn, right? So if we had to wait for this long mess of things to happen, which happens to take O log squared n messages, right? So if we had to wait for all this to happen, then we'd kind of be in a shitty position, right? Although we still have the other two requirements of what Chord says, which is provable efficiency and correctness. Now, we can kind of speed this process up a bit, that if we join the network, and we know S is our successor, we can just ask him for his finger table, and it'll be relatively close to what ours is. So that'll cut down on some of the messages, but it still doesn't work very well in a high churn environment. Sorry, I'm going to start talking quickly because apparently I'm running out of time. And probably start skipping some stuff, right? So it doesn't scale well. But the idea behind that was to kind of familiarize what it means for a node to join the network and then how we construct the finger table. So let's define a better method that allows concurrent joins and leaves to happen all the time, and still maintain the correctness and efficiency, and on we go. So the original method was very aggressive, and that's the word it uses in the paper, to maintain its finger table, and that it just figures it all out right from the bat. So what the better method goes to propose is that it takes the idea of the correctness and it takes the idea of the performance and separates the two. Because again, all we need for correctness is the successors. So a better join is that we still ask this node that already exists in the network, we still ask him, okay, who's our successor? And we kind of pop in there, right? But now we have these two different functions. Instead of like the 3 or so functions or methods we had before, all we have is stabilize and fix fingers, right? And both of them are run periodically. And these parameters can be tuned, their frequency of what they're run, basically, and those are based off of what your expected churn is in the network, right? So you can have this run all the time, or you can have it kind of run, every so often, and that depends on how often people are going to come and go. Right? So stabilize goes and asks the successor, our successor, who we know, because that's the only requirement, the only first thing we did, which is know our successor, right? So it tells our successor, and every node runs this code periodically, right? But in the context of the new node, let's just talk about that. So we ask our successor, okay, who is, I'm supposed to be your predecessor, right? Yeah, sorry, I'm going fast, I'm going to confuse myself. We ask our successor who he thinks his predecessor is, right? Ideally, it should be us, but if now a new node has joined between us and our successor, he's going to return some other guy, right? And if that's the case, then we know a new node is joined, and we now make him our predecessor or our successor, and then we notify him that we are his successor, right? So this actually maintains the correctness side of it. Now, fixed fingers, instead of actively right off the bat just kind of building up the entire finger table, what it goes through is that it's called periodically. It picks some random number between 1 and m, exclusive, inclusive, and then it just computes and finds, using find successor, who the node in that network, who that node in that finger table is supposed to be, right? So this just like it can be. This is usually run more frequent than this, but again, it's up to your application. And so the idea is eventually, right, if you have a decent random number generator with high probability, then we can generate an entire finger table. Right, so this is kind of the workflow. N joins, N notifies S that N notifies S, and S sets N as his predecessor, and then P calls stabilize, assuming that S should return back P as its successor, but it turns out there's a new node in the network, and now N is his successor. And that's kind of how that works. Okay, so what did we just get? We have correctness. We have correctness because we still maintain, the only thing we actually truly maintain when we joined is the successors, right? And with stabilize, we maintain the successors of our predecessors that now know who the correct one is. So we now have correctness. And we now have efficiency, right? Because eventually, fixed fingers is called periodically, we'll always know, and have an updated with like m many calls of fixed fingers, we'll know we have a full finger table. And if the network changes in some way, then if it's the case that our fixed fingers picks the random number that happens to be the node that has now changed, we'll either know that there's a new node in the area because find successor will return something else, or if it does, it's either a new node has come and the rest of the algorithm figures it out, or we know that someone's left the network. Right? In either case, we still maintain the efficiency because our fixed fingers method will generate the right finger for that ith entry. Right? But how do we add our failures, right? So there's a bit of a trick here. Right, so we're almost done, sorry. So to maintain correctness and maintain performance, what do we do in the light of failures, right? So new nodes is easy because if there's a new node, if we send to someone else, right? If I'm trying to talk to David, right? And I know the number of you that are in my finger table, but now there's a new node, right? So if I know the person, if I knew the person closest to David that was I know of my finger table, if a new node happens to join between him and David because he thought David was his successor, right? The only thing that's going to happen in terms of my request is going to take now one extra hop. That's it, right? Now it could be one extra hop for every new node that joins between you and David. Roughly. That's actually not right. Less than that number. At most that number, right? So if we maintain what we now call a successor list, right? Sorry, I'm doing overtime, whatever. I had no idea it would take this long. So if we now maintain what's called a successor list, which again has m many entries in it, which is every successor. So if in the successor list, right, to go back to one of these examples, I'll go back. So to go back to one of these, right, I know of my finger table because that's everything, all the gray lines are just finger tables, right? If I am A, I'm also going to know of my successor, but now I'm going to know of his successor and his successor and his successor and so on and so forth for m many down the road, of which m is still a relatively small number in the vastness that is the network, right? In the example, if we had, no, I won't go an example. Right? So if we maintain this successor list, and it turns out our successor fails, then if a network request comes to us, we can just go to the next person, the next successor we know of, right? Even if stabilize or fixed fingers hasn't run yet, we'll just know that, okay, node, he's failed, so let's just go on and try the next one, right? And there's some more subtlety in this, but I won't get into it, right? So failure and performance, right? So how does the finger tables kind of handle all this constant changing of failure stuff? So basically, when fixed fingers is run, it will figure itself out, right? But if it's the case that our fixed fingers hasn't run and it hasn't happened to get, because it's a random number, it hasn't happened to choose the right number, the right node ID, such that our fixed fingers is fixed for that node ID, it's the case that our lookup will fail, right? Which happens few and far between, right? But usually if it fails, it's either because there is some truly catastrophic fuck up in the entire network and just like everything is now partitioned and life doesn't exist. Or it's more likely the case that just our table information is out of date. And if it's out of date, if I thought Will was the closest preceding node in our finger table to David, right? But now William's failed, I'm just going to choose the next lowest person in our finger table who still precedes David because I now know he's the next person I now know of that's closer to David. Okay, so did we achieve our goal? Simple protocol functionality, relatively simple. I'd say yes. It's going through the paper. It's a relatively simple protocol. It's provably correct under high churn. There's another paper that kind of goes into some certain situations that Chord fails, but it requires very specific race cases. But under normal high churn, it works. It's provably correct. And under normal high churn, it's provably performant, of which that performance is O log n. Right, so what else did we get along the way? Load balanced, yeah, because of the hardness condition, the distribution of keys around the distribution of nodes and keys around the network is uniform. So there's no like small section or there's no weird kind of reaction to that. So we have load balance now around all the hash key or hash ring. It's decentralized because we have, that should be obvious. It's scalable because it always takes O log n, or with high probability, it'll take O log n. Number of nodes. So like in a million node network, it's still only going to take like 6 jumps to get the entire way through. And our availability is really good because even though I was going through it at the end really fast, in the event that nodes come and go, it still maintains provable correctness and provable efficiency. That's all, folks. Sorry if that took too long. Yeah, so I don't know what's happened now. You have questions, or we can get beer and then have questions. Or David knows what's up because he's coming to the board, or coming up to the front.
So thanks for talking about Chord today, John. Since we're a little bit over time, we're not going to do Q&A in front of the screen, but if you'd like to talk to John after this, and we can hash out any problems you have with Chord, we can do that. Cool.
I can get into the paper that kind of describes why some of this will fail.
Yeah, and I will open up the bar momentarily.